Okay, here's the review. So, really not going to do anything from Chapter 1. We're going to move on to Chapter 2, which was set theory. So there are a couple things about set theory. There was just the notation that we had. Actually, there was one thing that we did in Chapter 1, and it was on the first test, method of successive differences. So go ahead and review that. Most of you got that, did fairly well on it. So I'm not going to work through one. Go back to the first review. Basically have a list of numbers, and then you take the difference between each adjacent number, and then you create this upside down triangle, basically, until you get the same number at each on a row all the way across, and you work your way back up. So you can go ahead and look at that. Okay, so chapter number 2, there were different ways of representing information about sets. And sets are just a list of numbers, or really a list of any elements or members. And we used the notation. We could represent a set, and we would say a set is equal to, and we'd use these brackets. And let's just say it's the set of even numbers. So sets can be finite if they have a fixed number of elements in it, like this. So that's a finite length. There are 5 elements. The order is not important. So this set A would be the same as set A if I switched the position of some elements. It doesn't have to be ordered, they just have to be inside this set using these brackets. There's also examples of infinite sets where you sometimes establish a pattern of some sort. So for example, if I did 1, 3, 5, and you usually need at least 3 or 4, and then once I've established a pattern here, which looks like the odd numbers, then I would put 3 dots and then the right-hand bracket. So that's an infinite step that starts at 1 and goes all the way to infinity. You can go from the other direction as well. So if you start from the negative side, you go dot, 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 and you might have negative 7, negative 4, negative 1. And what you can see is I've set up this pattern that there's negative 3 between consecutive elements in the set. And so this would go to negative 10, negative 13, but we don't have to list them all. Now on the test, there was this case of list, it says using the listing method. So the problem said use the listing method to list the set of all integers. Let's do even integers between let's say 20 and 60. So when you're using listing method, you're doing something like this. You either list them all or you use some abbreviated version of it. Well, I don't really want to list 15 elements, so what I would do is I would write, I'd say set X is equal to, and what we do is we start at the first one that applies on the lower side. Now this is between, so that's where you guys got confused last time. When between means that it doesn't include the endpoints. So if we wanted to list this, we go to the next even integer, which would be 22. And then we would establish a pattern. And once we have established a pattern, then we would go dot, dot, dot to show the pattern repeats itself. And then we could either do, 54, 56, 58, but since we've already established the pattern, really all we have to do is put 58 in there. We don't need to show the pattern on the other side if we don't want to. So if that was between 20 and 60, if I did, how would I write it if I wanted to include, I could say greater than or equal to 20 and less than or equal to 60. If that was the set, then the notation would be, again, the brackets. You'd go 20, 22, 24. I've established my pattern, ... 60. So make sure you carefully read what they're asking for. Now, I might do something in this other notation, which says, so this is a listing method. This is a word description. And then you have this formalized set builder notation, which says it looks like this, and then it has a straight line. X is the negative integers. So what this reads as is C is a set of all X such X is a negative integer. I guess I could just say that. It's a negative. X is a negative integer. So if I said to do it in a listing method, this is a set building notation. The listing method again is this. I'd say C is equal to, and then I put the bracket. And because I'm dealing with negatives, it's better to have negatives go from right to left. So negative integers would be -1, -2, -3. So I'll put them in the exact opposite order here. -1, -2, -3. So I'm having it go that direction, and this shows that it goes on forever. So this is a infinite set in using the listing method. This is a finite set using the listing method. Okay, so that's then there were operations, set operations. So we had, let me just use some examples here. So that would be, that's intersection. And then you have, let's say, B, this U-looking thing, D. So that is a union. And then you have the complement. So those are the set operations. And so if you remember in the previous test, we did, I gave you the elements in the set. I'm not going to write it all out. You can go back and look at the second test, but, using letters to represent different sets like this. Okay, we'll do one example just so you know what I'm talking about. You can go back and look at this. So let's say B is B, C, F, G. So if I want to perform an operation between these two sets, I could do A intersect B. Now the intersection is the set, so the result is always a set, and it's a set of elements who are in both set A and set B. So these two elements, B and C, are in both sets. So that would be the intersection. Notice it's a set. It's the common terms between the two. When you do a union, say A union B, you list all the elements that are in both sets. So you can basically list out what is in A, and then you go to B, and you say, well, I've already got B and C, so I don't need to do it again. And have that. Now, to do the complement, you have to know what the universal set is. So this is it's not the same as this. This is a union sign. This is just U for universal set. So the complement of a set is equal to the elements in the universal set minus the elements in the set. So basically the complement is everything that's not in B but in the universal set. And then we had the problem like this. Again, you can go back and look at the test. And you can look at the review from this test. Remember, you can quickly page through those, or go through those reviews quickly and look for the elements that I'm talking about here. So I don't have to redo everything. So there's a problem like this where there are three sets, A, B, and C. And then I give you things like n sub A is some number, 35. So that's the number of elements in set A. That's really called the cardinality. That's the number of elements in set A. So that would be what's in this total set. And then I might give you some information about A intersect B. A intersect B is this overlap between set A and set B. And then I will give you some number there. And so there's a list of these things, and usually what you do is you start at the center, which is the intersection of all three sets, and then you go to these football-shaped things, because we already know what this side is, and then if we know the total, then we can take the total and subtract this to get that. So if you messed it up on the test, you need to look at it, because you're going to get it wrong again if you don't learn from your mistakes. So what you'll do is you'll basically fill numbers in here, and they're the number of elements that are in each little sliver of this thing. Now, I'm not going to give you one that involves words like the last problem on the second test, just because that takes a long time. So look at that on the previous tests. So I think that's it from set theory. Yep, that looks like about it. Okay, so then we went to logic. And I'm going to give you a logic. We did this both in, I'm going to give you a logic problem where you're going to have to fill out a table. So we had 3 or 4 of them. We had 3 on the second test and more on the third test. And so what I will do is I'll give you some kind of logic expression involving letters. And it will have 3 elements, 3 statements that have P, Q, and R. So make sure you know how to do 3 element ones. So what you're going to do, and again, you can go back and look at the previous reviews. So there's nothing really new. I'm just giving you an idea of the kind of problem that's involved. So you're going to have 3 columns that involve just the true and false values, that all the possible true and false values. Anyway, review that. Again, that's in both tests 2 and test 3, and there's going to be and, or, and, negation, and, if, then. So you need to know the truth values for these 3, 4 things. And, that's an or, that's an if, then, that's a negation. Okay, so that's that. Then we went on to geometry. So there's a couple of geometry things. One thing is we talked about, here I'm going to give you an example that we did in class. And then you have to just kind of think about that. We did a few examples in class. We didn't actually have this on the test. This is part of section 9.3. But if you remember, there was a question about what is the value of this area here if this has a radius of r. And the way we worked that was we used subtraction. So if the distance from here to here is r, then the side of each side of the square is going to be 2r. Because this is r, and then this is r, and you add them together to get 2r. So the area, you have the area of the square, and that's equal to the length of each side squared. So that's the area of the square. And then you have the area of the circle, which is going to be equal to pi r squared. So that's this area. And that area of the square is going to be bigger than the area of the circle because we got these extra little bits here. So the area of the rest, the total rest, meaning these four corners, is equal to the area of the square minus the area of the circle. So that gives us 1, 2, 3, 4 areas. To find the shaded area, you have to take the rest of the area that's left over and you divide by 4 because these are all the same size and shape, they're just oriented differently. So if you plug all that stuff in, you'll get the answer. So you plug that into what you've already done here. So all you really have to do is the final answer, the shaded area, is equal to 4r squared minus pi r squared divided by 4. What I did is I squared this. 2 squared is 4, r squared is r squared, minus pi r squared. I think the answer was, what they did is they factored out an r squared. So you get r squared times 4 minus pi over 4. So that's your area, shaded area. So that's kind of, it's definitely not going to be that problem, but it's going to involve something like that, simple shapes. So you'll need to know what the area of a triangle is. And that's equal to 1/2 the base times the height. You need the area of a rectangle. That's equal to just the base times the height. You need the area of a circle, which is pi r squared. And what else you might need? Square. Just use that. That's just equal to s squared. S is the size length. So I use that, this one here. I use that one there. So it might be advantageous to make sure you understand those because I could use those in the problem. So, and then there was the case, there's a couple of cases. Again, you can look back on the last, on test number 3, I guess it was. I think it was 3, maybe 2. No, it was 3. You know, we had these geometric situations. So, you know, knowing the relationship between these angle values, that's, you know, these angles here, the big angles are going to have the same value. And then the small angles are going to have the same value. So these are 2 parallel lines of transversal. I'm not going to put on one of those more complicated angle things, but I may ask you a specific question. So the other 3 cases are the interior angles of a triangle. So let's call this, let's say this is 40 degrees, this is 60 degrees, this one has to be 80, okay, because the sum of the angles, internal angles of a triangle equal 180, no matter what triangle it is. And then you have the case of the external angle of a triangle. So here's another triangle. And there are more than, let's call this angle 1, let's call this angle 2, we'll call this angle 3, we'll call this angle 4. So what we see here is we see a straight line with a ray going off of it. We know those are supplementary, so angle 4 plus angle 5. The measure, I guess, really the measured values of those equals 180 degrees. We also know that angle 4 is equal to angle 1 plus angle 2. Not equal to 180, but they're equal to the sum of these two angles, which are the opposite interior angles. So again, in the tests, we might have given you, give you some values. This is x, and this is x minus 4, and this is 2x minus 1. And in this case, you use the fact that the sum of the interior angles add up to 180 degrees. So there's two choices. They either add up to 180 degrees or they're equal to each other. I guess we could have complementary angles, but so those add up to 180. So if we do that, we'll get 4x minus 5 is equal to 180. 4x is equal to 185. So x is equal to 185 over 4. Since I just thought those up, that's why I got an answer that's not a nice integer, but just look at those problems that involved x values. Also, another one a problem that you might want to revisit and understand is this one in the third test. I'm pretty sure it's the third test. A lot of people got this wrong. And what you have is, because these two triangles are nestled within each other, they're similar triangles. So this angle here is the same as that angle there. These are both 90 degrees, and then this angle's the same because they're on top of each other. So what we saw there was, let's say I give you this. Let's pick another one. Let's say this is y. This length along here is y. And this whole distance here is 120 centimeters. And let's say this one is 60 centimeters. So the question, and this one is, let's say, 105 centimeters. So how do you figure out what this unknown length side is? Well, you've got two similar triangles. You get this triangle, and you got this big triangle. And these two sides correspond to each other. This hypotenuse, long hypotenuse, is, what's the word I was forgetting, corresponds to this shorter one, and then these two sides correspond. So what we have is you have the distance 105 centimeters. This side length, that side length is equal to, that's the big triangle. This is the big triangle. So you get 120 here, and y is the smaller side. And so you can cross multiply and solve for y. Now that one's actually easier than the one on the test, because if you remember the one on the test, this is the unknown. And I think I gave you something like these two separately. So let's say this one is 80, and this distance is 70. So you do the same thing. In this case, the longer length. So what we're trying to do, let's call that x, since I called it 1y. So the second kind of problem would be you take this length to x, which is this side of the big triangle, to this side of the small triangle. These are corresponding sides. You take the total length, not just 70, but the whole length, 150, divided by this length, 80. So it's this whole side of the big triangle and the whole side of the small triangle. And then you can solve for x. So think about that. Greatest common factor, using two methods that we did in the last test. So if you didn't remember what the two methods are, actually there were three methods, but we're not going to do Euler's method. So it's the prime factors method, in the dividing by prime factors method. You can look those up to see which one's which. And there's corresponding procedures to find the lowest common multiple, least common multiple. Then there's the prime factors method, there's the dividing prime factors method. Factoring, problem number 1, since some of you guys got it wrong, when you list the factors of a number, say of 72, you're not doing prime factorization. Prime factorization is when it says prime factorization. What factoring is listing all the numbers that are divisible, 72 is divisible by. So the way you do that is you write 1 and 72, which some people forgot to do that. They started at 2 instead. And then you go up larger numbers and you ask the question, can I divide this by these numbers? And I know this one does it, so I wrote it down ahead. So then you can just take this number, divide by that number, and match them up. So with the one on the test, 72 divided by 2 is 36, 72 divided by 3 is 24, 72 divided by 4 is 18, 72 divided by 6 is 12, and 72 divided by 8 is 9. And so that's factorization. Prime factorization, if I said do prime factorization, which you also need to know how to do, because you actually need it in both of these methods anyway. So whether I was directly asking it or not, when it says prime factorization, that's when you break it up into a product of just prime numbers. So the way I do it here for this number is I keep dividing by 2 until I get an odd number. Then I ask, can I divide that by the next prime number, which is 3? The answer is yes. And so the prime factorization, and you want to write this out in this form, exponential form, is that. So that's what prime factorization is. This is factoring. And then you can use this prime factorization in the prime factors method. You can review the last video if you didn't know what you were doing. Okay, we're almost done. Okay, let me just, and again, I'm just going to mention what some of these things we've already done before. Simplifying fractions. Actually, simplify rational numbers. So if you have 30 over 72, that's not in its simplest form. So you write these out until you run out of common terms that you can cancel out. Now, let's just finish it and then I'll explain something. So you can see it simplifies down to 5/12s because 30 divided by 2 is 15, 72 divided by 2 is 36. These are not both even, so then you go to the next number, which is 3. You can divide both of them by 3. So this is the final answer. If you were to go from here directly to here, I need to know what you divided by, which would be 6. So you need to show if you're going to skip the intermediate steps, tell me what you divided by. Because otherwise, you could enter this into your calculator, you get a decimal number, and then you could back it out using the fraction thing, and you get the answer without really knowing what's involved. Adding and subtracting fractions. We did that. That was the last couple of problems on the last test. And there is one of those more complicated ones that we had, like the last problem on the last test. Like 7/8 minus 1/3 divided by 1/4 plus 2/3 or something like that. So make sure you know what you do is you have to do you do the addition, subtraction of the fractions, come with the combined fraction, add the fraction to the combined fraction. Once you've completed all of this, then you take the reciprocal of the denominator, multiply it by the numerator, multiply it out, and then simplify it. Okay, what else we got here? convert. We did this on the last test. Convert decimals. This was the next to last problem to fractions. So, what we do is we take our decimal, we make that into a fraction. You multiply this by whatever number of digits. So this 30.35 becomes 35. And you can always plug this into your calculator and see if you get that back if you forget. So it's to make it something over 10, something over 100, something over 1,000, depending upon how many digits you got in your original number. And then you simplify it by finding a common factor, in this case 5, so you get 70 over 20. So make sure you show the step.
Okay, so here are the few additional items for the exam. So they're going to be one of these unknown angle diagrams. So you guys are pretty good at that. So I'm just going to have some lines intersected. You can look at previous review, but might have parallel lines and transversals and stuff like that. And I'm going to give you certain angles, and you're going to figure out the rest. There's also using truth tables for logical arguments, or to determine whether an argument is logical. So some of you guys had some difficulty with that. So it's using truth tables to show how do you spell show validity of arguments. Now I'm going to go into a little detail here because some of you guys just weren't paying attention. So what you have is some okay, so here is an example of using truth tables to determine whether an argument is valid or not. So the procedure is you have to define what the statements are. So I would say statement P is this first part. We have an if-then statement. If we are to have peace, then we must not encourage the competitive spirit. So statement P is defined as we are to have peace. Okay, the second part of the if-then statement is we must not encourage the competitive spirit. Well, I'm going to do the positive part. We encourage the competitive spirit. Okay, the third statement is we had to have progress. Okay, so R is have progress, to have progress. Okay, and you can see the second part of this if-then statement. We must encourage competitive spirit. That's in statement Q. The conclusion is we don't have peace. That's first, and we don't make progress. So now we need to create the corresponding logic statements for both the premises and the conclusion. So we're going to write premise 1, premise 2, conclusion. So the first one's an if-then statement. So it's if P, then if we are to have peace, so that's P, we must not encourage. So that's if P, then not Q. So that's premise A. So A is, I'll just put A, this is statement A. Okay, statement B, which is the second premise, if we are to make progress, so progress is R. So if we make progress, we must encourage the competitive spirit. So if R, then Q. And then C is the conclusion. Therefore, we don't have peace. So the therefore means that it's the conclusion. We don't have peace, so that's the negation of P, and we do not make progress, so that's the negation of R. So they are the symbolic logic versions of the three statements. two premises and the conclusion. These are all compound statements because they're a statement and a connector. Then what you do is you connect all those together. So you take premise 1 and you connect it to premise 2 with the AND statement. I'll let you guys forget the AND part. So that's premise 1 and, don't forget the AND, premise 2. So those are the two premises, and then you connect that to the conclusion using the conditional, which is the if-then statement logic. So we have not P and not R. So that's my conclusion. Then what we need to do is we need to make a truth table up, and we're going to need columns for P, Q, and R. And then you're going to need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So you're going to need 14 columns. And then you're going to need 9 rows because you have P, Q, and R. So let's do that. So we're going to need 9 columns and 14. So again, when you have this on the test, you're going to need to, I'll give you the table. And you have to determine how many things you need to use. You won't actually have to construct the table. You just have to decide how many of them you're going to need. Okay, so there's my truth table. And now we'll fill it out. So we've got P, Q, R. Then we have our logic statement here. So we have if P then not Q, and if R then Q. So those two premises, conditional, not P and not R. Then we fill out the rows. So remember, P, we do 4 trues, 4 falses, 2 trues, 2 falses. And then true, false, true, false. Okay, now we just fill in the columns, just copy down what we have in the first 3 columns, whether it's copying down or doing the opposite. So Q is true, true, false, false. So not Q is false, false, true, true. And R is true, false, true, false, true, false. And Q is true, true, false, false, true, true, false, false. Not P is false, 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 false. True, 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 true. And not R is false, true, false, true. So we alternating, but we're starting up with false, then going to true. Okay, so that's doing that part. Next, we're going to do these 3 columns, which is the stuff within the parentheses. So the if-then statement is only false if the first one is true and the second one's false. So you can see those 2 are false. True, false, true, false. And all the other ones are true because that's the exception to the true is the false, and that's when it's true and false. Over here we have the same thing. If R then Q, so we look for true, false. So we see there's one here. True, false is false. True, false is false. So those are the two cases of true, then false, and all the other ones are true. And then we do this one. So this is an and statement. So the only time an and statement is true is when they're both true. So that's both trues. All the other ones are false. Okay, next thing you do is you go between the two premises. So you compare the result of this, that's that column. You compare these truth values with those truth values with the and statement. So the only time these are both true, the only time an and statement is true is when they're both true. So here we have a case true, true, same here, true, 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 and this one's true, true as well. That's a true, true right there. Okay, so we got 3 trues, and the rest of them are false for the and statement. So again, the and statement is only true if they're both true. And then we compare this one with that one, put the answer in this column, use the rules for the if-then statement. So the only time that the if-then statement or the conditional operation is false is if the first one's true and the second one's false. So, when you have false first, you don't have to worry about it. True, false, so this one's false. This one's true, that one's false, so that's another false. Or 2 trues, 2 falses, 2 trues. Okay, so it's just these 2 that have true, false. And the rest are trues. So because we don't have a tautology, the argument is invalid because we don't have a tautology. Okay, so that's the example for. So just because you understand this example doesn't mean you can't just copy this down and know and say, oh well, I can use this, because if you don't understand the procedure, you're out of luck. And the final problem is just going to be the last problem is going to be something to do with the volumes. So just make sure you write down all your volume equations, and I'm going to give you one of the choices. A rectangular parallel pipette, which is a box, a right circular cylinder. So you have to know, I may not draw a picture, I just may use words, and you have to know what they look like. So you probably want to draw a picture of each one, what each one looks like, so that then you can use that to tell you what the variables mean. So the ones I want you to know are a box, a right circular cylinder, a cone, and a sphere. And just make sure if it's surface area, that it is units or squared units, and if it's a volume, that the units are cubed.